We've seen what the hydrogen atom energy levels look like, and now we're going to start thinking about what the hydrogen atom wave functions look like. And of course, you know the answer to this. These are the orbitals. These are the atomic orbitals that you've been studying for years and years and years. But now we get to see them as solutions to the Schrodinger equation. So the wave functions are going to be a function psi of r, theta, and phi, and we're going to use separation of variables, and we're going to proclaim that that's going to be some function of r that depends only on the variable of the value of the radius, r, capital R of r, multiplied by another function that's going to be, we're going to just call it ylm, and it's going to be a function of theta and phi. Now that ylm name ought to be pretty darn suggestive, because in fact we already know the answer to that thing. The angular part of the wave function, which has no potential associated with it whatsoever, we already solved that. And we just know that's going to be exactly the same as the rotational wave functions that we've been looking at before for molecular rotation, rotation of a molecule, rotation of electron about a nucleus. It's no different to quantum mechanics. There's a different reduced mass, but the wave functions are going to look the same. So the key is what these functions are, the radial functions look like, because there the potential is way different. Instead of a parabolic potential for a simple harmonic oscillator, we have this sort of 1 over r well hole that the electron is trying to fall into that comes from the Coulombic attraction. So it's a totally different beast. The next question is, what do we want to actually know? And basically the question we want to ask is the probability of finding Clarissa at a certain radius. So the question is, how far away from the nucleus will I typically find the electron? Will I find Clarissa? That's the most common working question. From time to time we might also want to know, where exactly is the electron? But most commonly we want to know in what region is the electron. And the first and simplest question is, at what distance from the nucleus do we find her? So the probability of finding the object at some distance from the nucleus, it's a probability, so not too surprising it's going to go like the wave function squared, so there's a capital R squared in there. But there's also the radius itself squared. So to find the probability of finding Clarissa at some distance r from the nucleus, we take that value r and we square it, and then we multiply it by the function, which is capital R, the big R, which is also a function of radius. And that's how we get the probability distribution. That's a little bit weird, so we want to look at it a little bit. And the main question is, why is there that r squared term? So let's look at r. Here's an axis, and we've got a radius, and we've got some unit 1 and some unit 2 here. They're just arbitrary numbers. You can think of them as maybe Bohr radii, because that's a nice number to think about. And let's think of a circle, or really a sphere, of radius 1. And then now let's think of another sphere, and it's got radius 2, and we're marking that in green here. So if I go 1 unit out, 1 Bohr radius out, so I'm going to chop this space up into constant angular chunks here, alright? So let's go 1 distance out and take 1 angular chunk. So I'm going to go up sort of what is that? It's pi over 8 away from the axis, and I'm also going to go out pi over 8 in the other direction, so I get this little patch or swath that I've indicated in purple here. And it's 1 unit of area there. Now let's go out the distance 2 and do the same thing. So we're going to take a swath, and we're going to go an angle pi over 8 in either direction, in the longitude direction and the latitude direction, the co-latitude direction. Okay, azimuth and co-latitude. We're going to go pi over 8 in each direction, but out at radius 2. So if I do that, I'm going to chop out the same swath area, but in that whole distance, I'm going to do that 4 times. So I've got 4 of those swaths out there now. Okay, so I've gone out twice the distance, but I've got 4 times the area. And basically the surface area of a sphere is 4 pi r squared. It goes like the radius squared. And so that is why the r squared term is in there. The real estate gets that you just get more space as you go farther away from the center of our spherical coordinate system. And you get more space, you get more points, you get more unit chunks of area proportional to the radius squared. So if I want to know just plain how far out from the nucleus am I, there's a lot more real estate way out there in the exurbs at an r of 2 than there is in the suburbs at r of 1, and a whole lot more real estate than there is way in the middle of the city at r equals 0. So it's easier to find a place to be at r equals 2, and even if the actual probability of being found in any one of those little colored patches may be a little bit lower, I've got many, 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 many more little colored patches out there, and so the overall probability of being at that radius can increase. So let's see maybe how this can play out here. So yeah, that's proportional to the area. There we go. So now let's look at the function as a function of r, and now we're going to put the Bohr radius in there. So we got a naught. It's about half an angstrom, and the function is always going to look like some stuff, and then there's going to be a term that goes like e to the minus a scale radius rho divided by the principal quantum number n. The function has always got this e to the minus rho over n term in there. And that stuff is actually going to be some polynomial. But that e to the minus rho over n is a really, really important characteristic of how these things behave. And rho is actually going to be equal to the nuclear charge z times the radius divided by the Bohr radius. And what this means is that if the charge is 1, then the sort of basic radial distance is 1 Bohr radius. So if our distance out is 1 Bohr radius, then rho is equal to 1 if the charge is 1. If the charge is bigger, then the scale distance gets smaller. Imagine the charge is 2. Then if I get to an r of a half a Bohr radius, a half times 2 is 1 a naught over a naught is 1. And so if I make a helium plus nucleus, if I make a helium 2 plus nucleus and put 1 electron next to it, then that 1 electron is going to kind of be twice as close to the nucleus as the charge, as the electron will be if I just have a single charge there. So that's our scaled distance. All right, and it goes of chunks of Bohr radius, and again, a Bohr radius is about half an angstrom. And there's always, always, always this e to the minus rho over n term. So let's just look at what that looks like. If rho is, if z is 1 and n is 1, then it's going to look like that. So it's going to go down like an exponential. Z is 1, n is 1, so it goes down to like 0.27 at a naught, and then 0.27 squared at 2 a naught, etc. So this exponential decay is something that you should just have cemented in your head as something you just intrinsically know what it looks like. Now, if I go to n equals 2, so if we increase the principal quantum number to the second shell, then I go down by 1 fold at 2 a naught. And so the exponential gets much more gradual there, and we get this green curve here. So what this exponential term is doing is it's basically snuffing out any polynomial there might be and driving it to 0. And so the purple z equals 1, n equals 1 exponential is snuffing it out fast. It's making it very hard to get any wave function density much beyond the Bohr radius. Whereas the z equals 1, n equals 2 green curve is much more permissive, and it's letting quite a significant amount of density exist all the way out to 2, 3, 4 Bohr radii without too much trouble. So it lets the function exist out to a greater distance. Now if I increase the charge by 1, and we go to z equals 2 and n equals 1, then we get this blue curve here, and that's where you sort of have the helium. The charge is drawing the electron Clarissa closer in, and you get a very, very tight exponential decay going down very quickly. So the n is determining the shells, because the n determines the characteristic distance of that exponential function that's pushing the wave function down to 0, but then the total charge is also going to vary things. And those are the broad essential features of these functions that you should be familiar with. So if we take that function, and now we look at this r squared, the probability distribution, we multiply by r squared, and we multiply the function itself, we square it. I take the same purple function there, which is just e to the minus rho, where rho is equal to just r over a naught. So what it looks like is roughly this purple distribution down here. So instead of having a maximum at rho equals 0, at r equals 0, it is a maximum at rho equals 1, at r equals 1 Bohr radius, a naught. That's where the probability of finding Clarissa reaches a maximum, because that's where you have the commodious overlap of the exponential decay, but also the fact that the real estate is growing as you head farther out. That's sort of the optimal distribution here. And so instead of a decaying exponential, you get this rather tightly peaked function that looks roughly like this purple function there. So that area, roughly around 1 Bohr radius, is where you're most likely to find Clarissa, even though Clarissa would dearly love to be right there at r equals 0. So the most likely place to find Clarissa, the most likely single point, is at r equals 0. But the most likely distance to find Clarissa from the nucleus is way out there at 1 Bohr radius, r equals a naught. And that's just there's much, much more space out there. So that one lonely point exactly on top of the nucleus, even though it's the most probable point, it gets utterly overwhelmed by the fact there's so much more real estate out at a naught that is sort of the best compromise between a reasonably high probability and a reasonably large amount of real estate, and that's where you get the maximum distribution. And that's really where we get these shells. So that the distance where you find Clarissa, when it's in the n equals 1 principal quantum number, is fairly tightly confined to a Bohr radius plus or minus a bit. If you go out to n equals 2, that much more permissive function actually comes up in the maximum by the time I finish squaring everything and adding in an r squared. It's all the way out at 4 Bohr radii. And so it's really way farther out. So there's a really, really big distinction between the most likely distance to find the n equals 1 electron. And then if we promote it up to n equals 2, it really jumps out into the exurbs, and it's out there at roughly 4 Bohr radii away from the nucleus.